Hi everybody! Today we'll summarize Unit 8, which deals with organometallic compounds containing metal-carbon multiple bonds. Following the syllabus, we will focus on metal carbenes, classification, and characteristics. However, remember that in this group of organometallic compounds containing multiple bonds between a metal and a carbon atom, not only carbenes and alkylidenes containing a metal-carbon double bond with a trigonal planar configuration for the carbon, but also carbenes with a linear metal-carbon triple bond are included. Once again, let's go back to the historical review we did on our first day class. And let's remember that it was in 1964 that Fischer's group prepared the first transition metal-carbon double bond, which he called a carbene. 9 years later, in 1973, Richard Schrock prepared the first early transition metal complex with a metal-carbon double bond, which he called an alkylidene. The reason that Schrock gave these carbene complexes a different name, alkylidenes, was not just because of the structural differences, but also because these early transition metal alkylidene complexes had very different, almost opposite reactivities compared to Fischer carbenes. In fact, Fischer and Schrock carbenes are the extreme cases of a series of compounds. Some complexes, of course, will fall in between either category and can't be clearly identified. There isn't any clear-cut way of distinguishing Fischer carbenes from Schrock alkylidenes. Fischer-type carbenes feature a substituent X, that is, a pi donor, by virtue of having a lone pair of electrons available to donate to the carbon atom, such as alkoxides, amines, and chloride. In addition, the tendency for such carbenes is to bind to low oxidation state transition metals with pi acceptor coligands, that is, those having an empty d orbital, such as on a phosphine, or an empty antibonding p antibonding orbital, as on a carbonyl ligand. These Fischer carbenes are regarded as neutral two-electron donor ligands in a singlet electronic ground state. Conversely, Schrock carbenes are lacking a pi donor substituent on the carbon atom, and as ligands are considered to be two-electron donors with a charge of 2-, the anionic, for purposes of formal electron counting and having a triplet electronic ground state. The metals to which these ligands bind are generally early transition metals in higher oxidation states and with coligands that are non-pi acceptors. Let's have a look at bonding, starting from Fischer carbenes. In a singlet state carbene formalism, the bonding description commonly used to describe Fischer carbenes is to treat the carbene as a neutral two-electron donor ligand. It has one filled orbital, sp2 hybrid, that donates its lone pair to an empty orbital on the metal in a typical ligand fashion. But it also has one empty orbital with pure p character that wants to interact with a lone pair of electrons from the metal in order to form a stabilizing bonding interaction. The metal d pi orbitals and those pi orbitals of the heteroatom, nitrogen or oxygen, or the phenyl group compete for the stabilization of the carbon of the carbene. This effect can be explained in terms of valence bond, considering a balance between the two resonance structures. Then, the actual binding order metal-carbon is lower than 2. Let's focus now on Schrock alkylides. A Schrock carbene forms two covalent bonds via interaction of the triplet carbene fragment with a metal fragment having two unpaired electrons. They are formed with early transition metals, that is, metals on the left of the periodic table, which are more electropositive and therefore whose d orbitals are of higher energy and in consequence better pi donors. That is the reason why each metal carbon is polarized toward carbon, because carbon is more electronegative than the metal. We can say that in the extreme case, the two electrons originally in a d pi metal orbital transfer to the carbon pi Z orbital, oxidizing the metal by 2 units and giving a Cr2 2- ligand, that is, a dianionic ligand, like an X2- ligand. This carbene, alkylidine, can be seen as a metal-stabilized carbon ion. In this table, both types of carbenes are compared. In Fischer carbenes, the carbon atom of the carbene behaves as if it carries a positively charge. It is electron deficient, electrophilic, and therefore undergoes nucleophilic attacks. In Schrock alkylides, the carbene behaves as a nucleophile, having a negatively charged carbon that undergoes electrophilic attacks because it is electron-rich. In Fischer carbenes, the metal center will undergo electrophilic attacks. Remember that it is usually a medium transition metal, not early, and therefore more electron-rich, especially with D6 counts, 6 electrons. In Schrock alkylides, it is an early transition metal, or at least a medium transition metal in high oxidation state, but always electron deficient, which will undergo nucleophilic attacks. Fischer carbenes are stabilized by heteroatom groups that can pi bond to it, such as alkylamines, alkyl sulfanyl, alkoxides, or phenyl groups. Schrock alkylides strongly prefer hydrogen or simply alkyl groups. Finally, let's remember, because we've just seen it, how these different carbenes can be obtained. Fischer carbenes can be prepared by nucleophilic attack as the carbon of a metal-carbonyl complex, followed by alkylation using a trialkyloxonium salt. While Schrock alkylides can be prepared by electrophilic abstraction of alpha hydride or by the protonation of a methyl ligand in a cationic complex. So we have finished Unit 8. Thank you very much for your attention.